All right, let's look at a double torque problem, otherwise known as a seesaw problem. Let's consider that these two children, there's two kids sitting on a seesaw, and here's the seesaw. Let's just make them boxes. How about that? And they're sitting on a seesaw. One of them is 3 meters away, and we're going to say that this kid, his mass is 30 kilograms. And we're going to say that this other kid has a mass of 45 kilograms, and we want to know how far from the fulcrum he should sit to balance the seesaw. All right, now you already know this intuitively. You know, and you can probably look at this and figure out that this heavier kid has to sit closer than 3 meters in order to get this thing to balance, because that will compensate for his greater weight. That's obvious. Now we're going to do the math behind it to prove it. Okay, so the question is, what condition has to be met for this seesaw to be balanced? Because you have these two objects that are applying a torque to this seesaw. This kid wants to torque the seesaw this way, and this kid wants to turn it this way. They're both fighting each other. And it may not be hard to see that for the seesaw to balance, both torques must be equal to each other. And that's where we start. Torque number 1 from kid number 1 has to equal torque 2 from kid number 2. And as we've already stated, and you should have written, torque equals force times distance. So I can substitute force times distance, or force, or FR, for each one of these. So the torque applied by kid 1 can be found by multiplying his force times his distance, and the torque by kid 2 can be found by multiplying his force by his distance. Alright, so we need the force and the distance from these two kids, and so I ask you, what is the force applied by kid number 1? And it may be tempting for you to look and say, well, his force is 30 kilograms, but it's not. His mass is 30 kilograms, but that is not the force. The force he's applying is his weight, the force of gravity. And the force of gravity is equal to the mass times the gravity. So I need to first of all calculate force of gravity number 1, which equals the mass of kid 1 times gravity. So that's 30 times 9.8. And if you multiply that, I think you get 294 newtons. And then the weight of kid number 2, which is his mass times gravity, which is 45 times 9.8. And if you multiply those, you get 441 newtons. So this is force 1, and this is force 2 from kid number 2. So those can go in here now. I now know my force number 1 is 294. I know my R1, that's the distance for the first kid. He's sitting 3 meters away from the fulcrum. Force number 2 is 441. And R2 is what I am solving for. So now I multiply 294 times 3, I get 882, and that equals 441 R2. And if I divide both sides by 441, I get exactly 2 meters, which matches what we said at the beginning. We knew that this kid had to be sitting closer to the fulcrum than 3 meters, and he actually has to sit 2 meters away for that thing to balance. This is as complicated as torque problems get in this class. These are double torque problems, also known as seesaw problems or rotational equilibrium problems, and this is about as complicated as they get. Just as long as you know that one torque on one side has to equal the other torque on the other side, that knowledge will get you where you need to go.